Welcome. 3-5, fitting a line to data. When data are almost on a line, it is often helpful to approximate the data by a line that minimizes the sum of the squares of the distances from the data points to the corresponding points on the line. So what we're going to have here is we're going to have a graph of a whole bunch of data points that almost look linearly. But what's going to happen is our calculator, if you remember from Algebra 1, our calculator is going to make a line of best fit. And what this line does is it helps us predict things, okay? Now, it helps us predict things based off of whatever our range of our data is. So if our range goes from 1910 to 2000, it's only going to be able to help us predict data from probably about 19 or maybe 1880 to about, I don't know, maybe 2050. And even then, that might be a far stretch, okay? Because what you don't want to do is you don't want your value to get out too far away from the data set that you have, okay? And we'll talk about that after a bit. The regression line. In Activity 1, you approximated a line of best fit for your data by eye. Okay, we're not doing that. How can you tell which line fits the data the best? If you pass your graph of ordered pairs around the room and asked each of your classmates to find the line of best fit, you might get many different lines as you have classmates. Okay? To solve this problem, statisticians have developed a method called linear regression that uses all the data points to find the line. A line found by using regression is what people call the line of best fit. It is also known as the least squares line or simply the regression line. So what you need to remember is this line has three different names: regression line, least squares line, and the line of best fit. You will learn how regression works in the later courses. For now, to find the line of best fit, we are going to use a statistics application. For details on how your application works, we're going to ask our teacher, which I'm going to show you here in Activity 2. Activity 2 says, Navy divers who remain underwater for long periods of time cannot come quickly back to the surface due to high pressure under the water. They must make what are known as decompression stops on the way up. If divers skip this procedure, they risk a serious medical condition known as the bends. The U.S. Navy has created tables that allow divers to know when and for how long they should stop on the way to the surface. The table below gives the decompression time needed, including ascent time, based on how many minutes were spent at a given depth. The points in the table are graphed at the right. Calculate the regression line for the decompression data. So if you look here, time spent underwater, if you were underwater for 150 minutes, that's 2.5 hours, correct? And approximately 40 to 60 minutes you would have to want to take to come back up to the surface. Okay? So, if you notice, my time spent underwater is my X value. My decompression time is my Y value. Okay? So, when you're looking at this table right down here, this is my X, this is my Y. So I'm going to click on my calculator, and you can do this as well. What's going to happen is you're going to hit Stat, Edit, which is number 1, or just simply press Enter. And I got some values in there, so I'm just going to clear them out. But I'm going to go in L1 and put every single X value that I have in here. So it goes 60, 70, 80, 100, 120, 140, 160, 180, 200, 240. Okay? In my L2, I'm going to put all my Y values. All right? 1, 3, 8, 15, 27, 40, 49, 57, 71. Uh-oh. I didn't get all the way up to the top. Oh, that's because I didn't clear out the other two. Let's try that again. 1, 3, 8, 15, 27, 40, 49, 57, 71, and 82. Delete that one. Okay, now if I want to, I can go to second function, stat plot. I can turn this on. Okay, what it's going to do is it's going to graph me those points as long as my window's big enough. Well, if you notice here, my window needs to go from at least 60 to 240 on my X. So I'm going to say from 50 to 240. Because I don't really need to see the rest, right? And maybe I should say 52, 260, 270. And we'll go up by tens. On my Y max, I need to go from my Y min, I need to be at 1, and it needs to go all the way to at least 82. So we probably need to stay at a negative 10, and let's go up to 100. And let's go up my scale by 10 as well. But what I'm going to show you is by turning that on, second function Y equals, by turning this on, it's going to graph my data points for me. And as you can see there, those lines look like they're taking a shape of a linear line. What we're going to now do is we're going to come up with a line of best fit, or our regression line. So it's going to predict a line that's going to be useful for all of those points. Okay? So I hit stat. I arrow over to calculate. And I scroll down to linear regression. You should remember this from Algebra 1, I hope. I press the number 4. I hit enter. Notice this is in Y equals AX plus B form, which is the same thing as MX plus B, our slope-intercept form. So my equation is Y equals 0.483. Y equals 0.483x minus 29.9. So let's go ahead and graph that and see how it looks against my data points. Okay, 0.483x minus 29.9. And since I still have those points, since I still have these points on my graph, I can see where that line is going through. And if you notice, it's pretty much touches all of them. Okay, it touches this one, this one, this one, this one, this one. You know, barely kind of touches this one, but we're not going to get all of them, which is why we just have this is a prediction equation. Okay, it's not going to go through every point, but what it's going to do is it's going to be the best line for your data to help you predict things. Okay? It says, as you can see from the graphs, that the regression line is a reasonable model for the data. Okay, like we said, it became very close. For each value of the independent variable, the difference between the actual value of the dependent variable and the value predicted by the model is called the deviation. Okay, the difference between the actual value of the dependent variable and the value predicted. Well, how do you find the value predicted? For instance, if we go back here, here is, let's use 120, okay? The actual is 27, correct? My predicted is based off of this equation. So what I would have to do is put 120 into this equation, okay? So let's go ahead and do that on our calculator. Or what we could do is look at our table, right? And what I'm going to do is I'm going to go to my table and I'm going to start at 120 because that's my point of interest. So I'm going to hit second function graph now. At 120 it says it's 28.06. Okay? At 120 it says it's 28.06. So if you look at this, 28.06, if you notice, is below, or 28.06 is higher than what 27 is, right? So as you can see here, when it says the difference between the actual value of the dependent variable and the value predicted. So we are subtracting 28.06, okay? That gives me a negative 1.06, okay? Which we would say is very close, right? I mean, we're talking about a point about right up here, right over the top of it, okay? The line of best fit has the following property. The sum of the squares of the deviations of its predicted values from the actual values is the least among all possible lines that could fit the model. This is why we call it the least squares line. So what they do mathematically, and it'd be a long process if you had to do it by hand, but mathematically what they came up with, go back to my graph, they came up with a line that used the least amount of distance from our predicted line to our actual points. And that is why it's called the least squares line. Thank you very much. That's all I have for you today. Please enjoy.